Hello everybody and welcome to the 8th 3D Buzz Math VTM. My name is Rob Rolnick, known on 3dbuzz.com simply as Demondo. And with me tonight, we've got... the sound of silence. Nobody. You see, it's 7 a.m. Jason and Logan just ever so recently went to bed. I'm not going to wake them up to record this. Zach isn't here yet, which is to be expected considering it's 7 a.m. And I guess that leaves me to record this one solo. I didn't record a Math VTM last night, and I figured more education is good for everybody, so why not? I'll hopefully not crash and burn while recording this, and let's see if I can pilot it myself. Anyway, might as well get started. 3D figures. In this, the 8th lesson, we're going to be exiting the planar, two-dimensional, flat world we've been talking about until now, and entering a three-dimensional world, so essentially that means we're going to be adding height to our figures. Although there are numerous such figures, meaning three-dimensional figures, we'll be discussing only a handful of them. We'll be dealing solely with special case figures. What does this mean? Well, one way to think of it is analogous to our discussion on quadrilaterals, or four-sided figures. We talked about the rhombus, the trapezoid, the parallelogram, and a couple others, but not every single possible four-sided figure. It would take too long, it would be almost impossible, if not totally impossible, it would bore you guys to tears. So we talked about the most common ones, the ones you come across most often. Similarly here, we're going to be talking about the three-dimensional figures that you come across most often, that you come across in mathematics quite frequently, in constructions, stuff that you see fairly often. So, on this slide, we have 4 of the figures we'll be talking about. These aren't all of them, but they are the cube, the cylinder, the sphere, fear, and the pyramid. So, moving on, we'll start our discussion with prisms. A prism is formed by connecting all vertices, or endpoints, on 2 congruent and parallel polygons. When the 2 polygons are connected by perpendicular lines, or lines at 90-degree angles, it is known as a right prism. Otherwise, it is known as an oblique prism. So let's examine this point by point. You're connecting all the vertices. This means that this vertex here is connected to the equivalent vertex down here, this one here to the equivalent vertex down here, and so on. What about part 2, with the whole thing on right prisms and oblique prisms? Well, let's jump to Photoshop quickly and talk about that. If you recall our discussion on squares and parallelograms, you had a stick figure pushing a shape. Well, here too, you have your stick figure guy, and he walks over to a shape, a nearby shape, and he starts pushing on it. So here's him pushing on, I guess I'll make it's supposed to be a cube, it doesn't look like one, but oh well. So there's a cube type shape, and he's pushing on it. Well, as he pushes on it, it slants, and it becomes another shape. In fact, let's say something like this. And yeah, it kind of grew in the process. It's a magical, cubey shape thing that looks horrible with my drawing skills, or lack thereof. In any case, that's the same figure. And here's the same stick figure guy, pushing on it still. He grew as well, and his face got kind of, dilapidated. But you'll notice that it slanted. Well, when it was here, all of these lines were connected to the polygonal top and bottom, the polygonal bases, at 90-degree angles. So there's a 90-degree angle up there too. Now, none of these lines are connected to the polygonal bases at 90-degree angles. So it started off as a right prism with right prism, meaning the lines connecting the top and bottom pieces are at 90-degree angles to those top and bottom pieces. And here, when it's an oblique prism, that's not the case. There's no 90-degree angles in the lines connecting the top polygon to the bottom polygon. So I'll just clear out this Photoshop and jump back to our PowerPoint slides. The volume of a prism is equal to the area of the base times the height, whereas the surface area of our prism is equal to the sum of the area of all the faces. So in this prism, to the bottom left, we're going to have 7 faces. There's this top one up here, the bottom one you can't see down here, which would be something like that. 2. There's a third one here, a fourth one here, one back there. That should be 5. 5. One back there. 6. And the final one over here, 7. So as you can see, there's 7 faces. And if you add up the area of each of the faces, then you'll get the total surface area. So, moving on, we have right prisms made from regular polygons. When discussing a right prism formed by regular polygons, then the following holds true. Like before, the volume is the area of the base times the height. The lateral surface area, which is something new, is simply the surface area ignoring the bases, meaning the top and bottom pieces. So it's the height times the perimeter of the base. And if you wanted to think about it, you can say you're adding up all the side faces, because if you add up this length times the height, plus this length down here times the height, times plus all the other lengths of all the base fragments times the height, you're going to have the perimeter of the base times the height if you factor out the height from all of that. Meanwhile, the surface area is 2 times the area of the base, because the polygons at the top and bottom are congruent. They're equally sized. So 2 times the area of the base plus the lateral surface area. So the perimeter of the base times the height. Now we're going to talk about, in Photoshop, we're going to talk about 2 very special prisms. There's the cube, which I'm hoping I'll get a little better artistic skills when drawing. Okay, it doesn't look like a cube, but it is. Actually, it looks so much like a box, we'll treat it like a box. We'll come back to the cube. So this box has a length called L, a width called W, and a height called H. Well, the volume is simply the length times the width times the height. So that's the volume. Vol. Meanwhile, the lateral surface area is the surface area of all the sides. Well, that would be lateral surface area, ELSA, equals width times height for this face, and for the face opposite it here, which would be back here somewhere, it's also width times height. And then for this face in the front here, it's plus length times height, and similarly the one in the back is also going to be length times height. So we're left with 2 width times height plus length times height. If you wanted the total surface area, so the surface area is simply the lateral surface area, 2 width times height plus length times height, plus the area of the bases, which would be, you're going to have 2 of them, so I'm going to keep it inside the 2 times, and it's going to be length times width. So that's what happens when you're dealing with a box. But what happens when you're dealing with a cube? Hopefully I draw it better this time. So now we have a cube. Like the box example, all of the angles are 90 degrees. And unlike the box example, all the sides, I'm not going to draw I guess I might draw a line through all of them, are the same length. We'll call it S. So, side length, side, equals S. The area of any face, area O face, is equal to S squared, which means the lateral surface area, ELSA, is 4S squared. The total surface area is 6S squared. 4S squared because you're only looking at the four sides. 6S squared because you include the top and bottom. And the volume, vol, is S cubed. So, if the side length was equal to 3 units, then the area of a face is 3 squared, so 9 units squared. Units squared. The lateral surface area is 4 times the area of a face, so 4 times 9, which is 36 units squared. The total surface area is 6 times 9, which is 54 units squared. And the volume is 3 cubed, which is 27 units cubed, in the case of a cube. So, with all of that covered, we're pretty much done our discussion on prisms, and we're going to move on to a discussion on cylinders. A cylinder is simply two congruent, parallel, and closed planar figures with their perimeter or circumference joined. So, I'm going to come back to that to explain it. I'll do it in Photoshop, but for now we'll move on to the next 2 points. A right cylinder is formed when the bases are directly on top of one another. It's kind of like the concept of the right prism. So an oblique cylinder would be if they're not on top of one another, if there's some skewing going on. Whereas a right circular cylinder is a right cylinder with a circle as its base. The formulas below are for such cylinders, meaning right cylinders. Right circular cylinders. The volume is pi r squared times height. Well, if you recall, pi r squared is the area of a circle. So it's the area of a circle times the height, meaning the area of the base times the height, so it's exactly like a prism. The surface area of a right circular cylinder is 2 pi r times r plus h. So it might be easier if we distribute that. And when you distribute that, you get 2 pi r times r, so r squared, plus 2 pi r h, or r times h. Well, pi r squared is the, like I said, the area of the base. So because there's two bases, the top and bottom, 2 pi r squared is the area of the bases. Which would mean, like you see below, the lateral surface area has to be 2 times pi times r times h. But how would we know that? Well, you know the circumference of the circle is 2 times pi times r. That's the circumference of the circle. And h is the height of the cylinder. So what this means is that if you unfolded the cylinder, you unrolled it, or at least the lateral surface area of the cylinder, that piece there, you unfolded it, you'd be left with a rectangle, the height of which is h, because it's the height of the cylinder, and the length of which is the circumference of the circle, 2 pi r. So that's how you work out the surface area. Now let's go back to the top part. A cylinder is simply two congruent, parallel, and closed planar figures with their perimeter or circumferences joined. So I'm going to jump into Photoshop, like I said, and explain that. Often you'll see the right circular cylinder as I showed on the PowerPoint, but that's not the only type of cylinder. Say you had, I don't know, almost a Pac-Man-y face here. Kind of like a Pac-Man face. And you had another one down here. And it's the exact same congruent, same size figure. And the perimeters of them were perfectly joined. It's a horrible drawing, but imagine it kicked ass. Well, as you can see, or imagine, because it's kind of hard to see it, that would form a cylinder also. And as such, so long as you have as long as the bases are a closed figure, meaning there can't be any opening, can't be something like that, and joining that to something down here, because it can't be like, that wouldn't work, because how would you join it? You'd have a big empty region here, and it would make it all weirdly hollow, and it'd be impossible almost to do. So that's not considered a cylinder. But if you were to join it like that, in fact, when you're making a 3D figure, it'd be almost impossible to have a non-closed figure. In fact, I'd even go so far as to say it would be impossible to have a non-closed figure as one of the bases, just because of the nature of a 3D figure. So, assuming this was the bases, since they're closed, if you joined them, their perimeter or their outside lines, the lines that you use to draw the figure, then you'd end up with a cylinder. So essentially, it's a prism, but the base doesn't have to be a polygon. That's all it means. Pyramids. A pyramid has a polygonal base. All the vertices on the polygon are joined to a single point in space outside the polygon's plane. So, let's see what that means. Well, the base of this pyramid is a square. All this means is that, you see all the vertices of the square? You go to the apex up here. This apex can't be on the plane of the square. It has to be above it, or to the side of it. It could be out here somewhere, and you could join all the vertices to that point. But it can't be in the plane of the square. So anyway, if the apex, or peak of the pyramid, is directly above its centroid, or the center of mass, then the pyramid is known as a right pyramid. Otherwise, it is not known as a right pyramid. A regular pyramid is a right pyramid with a regular polygon as its base. So you'll see how I color-coded. A right pyramid is in red. That means that the formulas below, in red, only apply to a right pyramid. However, the volume applies to all pyramids. A volume is simply the area of the base times the height divided by 3. Or you could say 1/3 of the base times the height. Meanwhile, when talking about right pyramids, the surface area is equal to the base plus a half of the perimeter times the slant height. Well, what does that mean? What's a slant height? If you see this green triangle inside the pyramid, if you look at that green triangle, you'll see that there's a small circle drawn inside the triangle, drawn inside the pyramid, such that the circumference of the triangle touches all the sides of the pyramid. In any case, if you go from the center, or the centroid, of your pyramid's base to the point where the circle touches the perimeter of the base of the pyramid, so here, from here, and then you also put a point at the apex of the pyramid, and join the 3 points, you get a triangle. I'm not going to do it, actually, because you already have the green triangle. The hypotenuse of this triangle, which I did just highlight in red, the hypotenuse is known as the slant height. So 1/2 of the perimeter times the slant height plus the base is equal to the surface area. But you also see that the lateral surface area is 1/2 of the perimeter times the slant height. So I'm going to quickly clear all the ink on the slide and explain that. Well, let's say let's say we ignored actually the perimeter piece. We ignored that, and we did it in pieces. Well, we'll call this piece here piece 1, piece 2, piece 3, piece 4 is back here. Well, since we're dealing with right pyramids, that means this the peak, the apex, is directly above the center of mass or the centroid. This means that all the slant heights are going to have the same length. So, I'm only going to illustrate this for one piece of the pyramid, and you'll have to take my word on it for the others, or you can do it yourself. This triangle here, the big side of the pyramid, is piece 1 of the perimeter times the slant height divided by 2. So base times height, height being the slant height, and piece 1 being the base, so base times height, piece 1 times slant height, divided by 2, gives you the area of that triangle. Well, if you repeated this process for piece 2, 3, and 4, so you said piece 2 times the slant height divided by 2, plus piece 3 times the slant height divided by 2, plus piece 4 times the slant height divided by 2, and then you factored out the slant height and the divided by 2. You'd be left with piece 1 plus piece 2 plus piece 3 plus piece 4, which is the perimeter, times the slant height divided by 2. Hence why the lateral surface area is simply 1/2 of the perimeter times the slant height divided by 2. So a cone. A cone is a closed figure with a single base that converges to an apex outside of the base's plane. So, what this means is that if you think of the analogy between a cylinder and a prism, where a cylinder doesn't have to have a polygon as its base, it's the same thing for a cone, the relationship between a cone and a pyramid. A cone doesn't have to have a polygon as its base. It's frequent that it has a circle as its base, but it can be any such figure that isn't a polygon. So, or any such closed planar figure, flat figure. A right cone has its apex located directly above the base's center. A right circular cone, which is what we'll be dealing with, is a right cone with a circle as its base. So once again, I color-coded. The volume of a cone, like the volume of a pyramid, is the base times the height divided by 3. The total surface area of the cone is pi times the radius plus the slant height. So, the lateral surface area is the pi times the radius times the slant height. So let's analyze these two. The easiest way to do that is to distribute the equation for the surface area. You get pi times r, meaning the radius, squared, because radius times radius is radius squared, plus pi times radius times slant height, s subscript h. Well, if you think about it, the base is pi r squared, because it's a circle. So that takes care of the base. And the slant height is really simple. It's, like before, it's the radius times the radius and height make a right triangle, with the slant height being the hypotenuse right there. So pi times the radius times the slant height will give you the lateral surface area. And lateral surface area plus base gives you total surface area. Sphere. A sphere is defined as all points on a sphere are equidistant from its center. So if you remember a circle, all points on the circle in 2 dimensions are equidistant from the center of the circle. Well, similarly, if you extend that into into 3 dimensions, and you get another circle, say here, then if all the points in 3 dimensions are equidistant from the center, then it's a sphere. And once again, the center, let's say, would be somewhere in there. And from the center to the outside perimeter, or whatever, is known as a radius, even in 3 dimensions. Radius. So, the volume of a sphere is really, really simple. 4/3 times pi times radius cubed. And the surface area of a sphere is 4 times pi times radius squared. Really simple. There's not much to know about spheres. ellipsoid. An ellipsoid is defined such that all cross-sections are ellipses, or also known as ovals. So say this shape. All the cross-sections, which basically means if I took a blade and cut it my ellipsoid like that, the piece I'd get would be an ellipse in shape. And if I cut it, say, like this, the piece I'd form, the cross-section, would also have an ellipse shape. No matter how I cut it, I'd always get an ellipse as the cross-section. So, if I erase all the ink on the slide, then you can read the little comment I put in brackets. You can think of an ellipsoid as a hamburger, so it can be kind of like pretty wide and flat, or it can be a cigar, so narrow and long. Well, when I said flat, I didn't mean completely flat. I just meant, not that tall. Or you can think of it as a stretched out sphere. So if you took a sphere, like a beach ball, and you applied pressure to it and it kind of deformed a little, that would be an ellipsoid shape. So there's 3 radii in the ellipsoid. Or I call them radii, but I don't know, that might not be the proper term. It's the vocabulary I use. There's one that goes from the center upward to the top. We'll call that R1. There's one that goes from the center to the side. We'll call that R2. And there's one that goes from the center out toward the viewer. So something like that. R3. Out of the screen towards us. In any case, if you take 4/3 times pi times R1 times R2 times R3, you'll get the volume of your ellipsoid. And if R1, R2, and R3 are all the same, then it'd be 4/3 pi R cubed, and it'd be a sphere. Meanwhile, the surface area of an ellipsoid is really complicated. It actually, I believe it requires a bit of calculus, and we're not quite there yet, so it's outside the scope of this lesson. Don't worry about it. A torus. For our purposes, a torus will be a donut-shaped object obtained when revolving a circle along an axis that does not intersect with said circle. So that's a lot of words to mean something really simple. I'll show you in Photoshop. Say we had a circle. A circle here. That's a beautiful circle. And you were revolving it along this line. So your circle is spinning along this line. Well, it would go in a pattern something like that, which is, again, not the best drawing, but that would be the pattern. And any cross-section, or depending on where you took it, but if you took it in a specific way, any cross-section, as you may see, would give you this circle. You can get, so if you look back, you can see that these cross-sections here, like this one here, or this one back here, give you circles. So you can think of it also kind of like a ring shape. Wow, if you just heard a loud thump, that was me accidentally smacking the microphone around. So, sorry about that. But anyway, you can think of a torus like a ring shape, or a donut shape. The reason I say for our purposes is that it is possible that there might not be a hole, and other such oddities can occur, depending on where the line is that you're revolving around. But, let's say the line was right tangential to the circle, there wouldn't be a hole, because it would be perfectly tangential that you're revolving around, so your circle would, the other half of the torus here would be touching the first half. So, if you can't see that, don't worry. Like I said, for our purposes, it's simply a donut shape. In any case, the volume of the torus is 4 pi R1 times R2. Well, what's R1 and R2? Well, I'll clear all the ink on the slide and show you. R2 is simply from take any circle. So we'll say we're taking this circle here. From the center to the circumference, that's R2. Meanwhile, if you're using this big circle out here, from the center, granted that's a horrible circling action that I did, to the center of the torus is R1. So from the center of the circle to center of the torus, actually it doesn't even have to be a circle out here. It can be the same circle we used here for when we used R2. It doesn't have to be the outside, the big circle I drew that was ugly. It can be this small one that was nicer. So from the center of that circle to the center of the torus is R1. And the other one from the center of the circle to the circumference of the circle is R2. So 2 pi R1 times R2 squared is the volume. Well, if you think about that, 2 pi R1 is the circumference that you'd have of the torus if you go from the exact center point of, let's say you did all these circles that I have in R2, and you did all of them for the whole torus, and you did the circumference that you'd get from that circle. I'll erase all the ink on the slide and show you again, because it's kind of really messy right now. If you went from the center of each circular cross-section and did the circumference of the torus like that, something like that, then if it's from the center of every cross-section, then you'd have 2 pi R1. If you multiply that by the area of any of those circular cross-sections, you'd have R2 squared times pi. Multiply that out, you'd get 2 pi squared times R1 times R2 squared. Meanwhile, the surface area of a torus is 4 pi squared times R1 times R2. And now for some exercises. Find the volume of a house constructed from a cube with a square-based pyramid stacked on top of it. The length of the house is 10 units, and the height is 15 units. So the house would look something like this. You've got a cube as the base, and pyramid for a roof. Something like that. And you know the length of the house is 10 units, and the height is 15 units. Question 2. Given a volume of 30 units cubed, would a sphere, a right cylinder of any height and any size base, or a cube have the least amount of surface area? Here's the tip. Granted, you can't easily calculate a cylinder for any height and any size base with a volume of 30 units. It would be very, very difficult. Instead, take a cylinder with a huge height and a small base that has a 30 units cubed volume, or one with a very, very large base and a very short height that has a volume of 30 units cubed, and see which one has, of those, the sphere or the cube have the least amount of surface area. And finally, what volume would a cone have by rotating a right triangle to the right, as illustrated? So you'll see that you're rotating along here, so you're going to get a cone like that, and that, and that, and so on. So you're going to get a cone like that. Now, when you're only looking at the right triangle, so it's a right triangle, I guess it's not going to come out well on camera. I'll just grab the black ink and the right triangle. The height of the right triangle is 4 units, the base is 3 units, and the hypotenuse is 5 units. Using this information, calculate the volume of the cone that you'd be forming. And with that wraps up this lesson. Thanks a lot, guys.